Okay, thanks everyone for coming today to our Beyond Scope, our first one for the fall semester. Welcome both online and in person. So fun. This will be recorded, so you'll be able to listen to it later if you want to as well. For today's talk, we have Milan giving a talk. He did his undergraduate work in the Czech Republic at Masaryk University. From there, he went to Brno University of Technology, where he did his doctoral work. He worked quite a bit with the Institute of Physics Materials, quite a bit there in Czech Republic, doing that work. During that time, he actually, when we first got to know him, he came here for about a year, to CMAS to do some of that work. Went back, and then we luckily got to come back for a couple of years as a postdoc, now with Mike Bell's group. So Milan's been here for 3 years doing a lot of great work on mainly the STEM instruments, and he's going to present some of his work that he's been doing looking at multi-scale characterization of 3D printed materials in STEM.
Thank you very much for introduction, Dan. Good morning, everyone, either in person or online. And welcome to my presentation from the Beyond the Scope series. Today I'll be talking about how we use CMAS as a facility to find answers to our questions in the field of material science and structural materials. And I know my topic of my talk is about 3D printable ODS-MPEAs, but today I want to focus on giving you some examples from point of view of user of such facility, like what kind of data and what kind of techniques you can use to find solutions for your open questions in whatever you're doing. So I am a member of a research group of Professor Michael Mills, and our main focus of our group is structural materials. So what are structural materials? Structural materials are among oldest fields associated with existence of human civilization, and the main role of this field is to preserve structural integrity of components, which are operating in specific environments where they're acting forces, high load temperatures, corrosion, oxidation, radiation, etc. And it's more a fact that structural materials basically enable existence of vast amount of functional inventions and devices which are essential for our civilization. For sustainable future development of our human society is heavily dependent on permanent effort to improve energetic and economic efficiency, especially in transportation or electric power generation and so on. And the role of material science in this overall goal of our society is that there's a permanent need to develop and offer new, better performance, cost-effective solutions in the field of structural materials. So modern material science engineering and materials design is heavily associated with multi-scale experiment and modeling validated approach, where before you get to the final component, as you see on the right, turbine blade, you have to start from nanoscale. You deal with atomistic simulations, you study dislocation cores and their structure, or chemical composition changes in the alloy on the nanoscale. Then you can move on microscale, where you focus on different properties of the alloy, and you can study dislocation precipitate interactions or defect interactions on a longer scale of grains. Then on mesoscale, you focus on physics-based crystal plasticity. You move more to scanning electron microscopes to find answers for your questions in this length scale. And then finally, we are dealing also with microscale, where we can do some modeling of bigger parts of components of using finite element scale we use some mechanical testing to validate the performance of the design, the material. So within this approach, nowadays, multi-scale characterization by various electron microscopy methods plays an essential role in delivering and connecting that information which is obtained at different length scales, and its critical aspect in modern material design. One of the recent examples of such development of new structural material is NASA developed a GRX 810 alloy, which we had privilege to be part of, and this new advanced material combines several state-of-the-art and hot topics in material science, which is additive manufacturing, multi-principal element alloy concept, oxide-dispersion-strengthening, and integrated computational materials engineering. And our participation in this project is a very nice example how this facility can be part of state-of-the-art research and current development, which can contribute to development of human society. So within my presentation, I'll use GRX 810 as one of the examples, like what type of electron microscopy-based multi-scale characterization techniques can be used, and what kind of role they can play in development of new materials as this alloy. So here's a short outline of my talk. I'll focus on 3-4 selected topics. I'll start with STEM diffraction contrast imaging, since we deal with structural materials and defect analysis. Then I'll talk about transition from STEM DCI to atomic resolution HDF STEM. And then I'll talk about some supporting techniques, complementary or techniques which can be cross-correlated with different STEM techniques, as a center of symmetry analysis or Stereostem Imaging. And I'll show you some examples, what kind of information we can collect and gain using these techniques in the field of structural materials. So let's start. So as I said, we are dealing with multi-scale characterization of metal samples. We are dealing with metallurgy, and in a lot of cases, we have sample which is quite large. It's from mechanical testing machine, and we have to go from this microscopic length scale to nanoscale. So how we do that? So traditionally, we use jet electropolishing. So we cut a piece of material, we polish it down to a few hundred micrometers, and then we electropolish, and we can use it in our state-of-the-art systems. In some cases, obviously, this is not the appropriate approach. So we use a workflow consisting of SCM systems and dual beam systems with focused I-beam, where we first use backscatter electrons and ABSD to select our area of interest in our metallurgical sample, and we extract oriented and size-specific FIB foil. Why that's important, I'll mention that later when I'm going to explain our approach to STEM. But we do that, for example, to make our life easier later when we are sitting in a probe-corrected system, that our foil is already prepared, for example, without any needing of tilting of the sample. We already have low index zone axis ready, and we can start our characterization. Regarding systems, all techniques I'll be talking about in today's talk, we do using two Titan TMIS systems. One is older image corrected system, and one newer one, TMIS Z with probe corrector monochromator. All these techniques I'll be showing to you, we use these systems for that. So let's talk about diffraction contrast imaging. We know diffraction contrast imaging as one of the oldest and started methods for imaging strain fields of planar defects in conventional TM. We know it's based on Bragg scattering of electrons which are dispersed from non-perfect parts of the crystal. And then we can use objective aperture to create a contrast. One of the type of defects which we investigate is dislocation. Usually in the conventional TM, we work in two-beam dynamical conditions where diffraction is occurring only from one set of HKL planes. So that's quite standard and known, and still a lot of people in the field of metallurgy use conventional TM diffraction contrast. When we go to STEM, so defect analysis using Bragg conditions is similar to CTEM. And all conventional TM rules for diffraction contrast are fully applicable now in STEM. But there are a lot of advantages over conventional TM. So some of them are, we have muted band contours and fringes. We can do much thicker samples than in conventional TM. We can do multiple imaging modes where you just turn the knob and you transition from attaining resolution, small field of view, large magnification, to a large field of view, low magnification diffraction contrast. We can do zone axis imaging, which this is usually a starting point for us in our workflow, where we start usually with zone axis first, and then we tilt to two-beam conditions. We have much greater signal-to-noise ratio, especially using now software tools as Thermo Fisher drift integrated frame integration function, which can be applicable for all different STEM modes. We can obtain very nice signal-to-noise ratios in STEM. And last but not least, we have uniform illumination over large field of view. So for thick samples, you start usually you can image basically the whole grain, and then you go to smaller landscapes. So a lot of benefits, and I'll start now with so-called low-angle annular dark field diffraction contrast in STEM. So we tilt our crystal into zone axis, and we focus on creating image and creating contrast using exclusively elastically scatter electrons to low angles. So we work with either bright field detector or annular dark field detector, and we form the image. As you can see, here is example how just simply changing camera length, changing the type of electrons which we are collecting to our detector and type of electrons which are creating our image, we can heavily affect visibility of our defects. So that's huge advantage that you have your crystal tilted in zone axis, and you can transition from Z contrast, eventually atomic resolution, to defect contrast just by switching the camera length. Here's another example how this looks like. This is nanocarbides, nanocarbonitrides, and steel. And these features are large, like 5-6 nanometers. And if we use Z contrast, it'll be fairly difficult to find them. So we start with a large field of view. We set our system so we have diffraction contrast, strain contrast emphasized, and we very nicely can find where the location of these nano precipitates are. Then we focus on them, and we can change the Z contrast to emphasize the mean square atomic number of the structure, and continue with atomic resolution study. So this brings me to example 1, where we used diffraction contrast imaging of the structure that's for the GRX alloy, where we just simply started, or we exclusively started with zone axis imaging and to get all possible G's, creating the contrast in our image. And this is ultra-polished disc foil. This is several hundred nanometers thick, and the image was obtained with probe corrected TMSZ. So producer of the probe corrected system usually advertises the system as state-of-the-art atomic resolution, few tenths of picometers resolution, but we use these systems. We use the systems for large field of view, diffraction contrast imaging to obtain such information about the microstructure. So when you cross-correlate with other techniques like EDS or atomic resolution imaging, you can get information about the dispersion of different features, structural feature, like where the oxide particles are, where the unit dislocation lines are, where the stacking fault tetrahedra are, where the dissociated faults are. And this is what's differentiated here by color. So this is zone axis imaging. And now let's talk about different case. This is a twin ACP embryo, which is sitting in a slip band in fatigue chrome cobalt nickel alloy, which is kind of like which is associated with GRX alloy. And let's talk about how we can use the STEM DCI to get different level of information about such a structure, which then have implication for study of mechanical properties of such alloy. So here you can see a video which is composed of 3 different diffraction conditions. So the crystal was tilted into 3 different tilts, and we are using for two of these conditions, which are two beam STEM DCI. We are using a G01 -11, and then we tilt to zone axis. Zone axis was our starting point, but since the structure which we are interested in and was tilted into zone axis, we wanted that to tilt a little bit to the angle so we can see the features which we are interested in. So this is classical approach, and you can see that in this bright field STEM diffraction contrast. This gives us the same opportunities as was in past, and with conventional TM, we can see the defects very nicely resolved. And if we focus to individual dislocations, when we take a look at this map, and this is what when I was talking about using site and orientation specific fit foil preparation, this is what you can reach. So if you prepare the sample properly oriented already using your dual beam system, then you know what to expect, what kind of opportunities you'll have to collect the information about defects in your studied crystal. So here we know that this on the map of reciprocal space on the left side of the slide, you can see that you have plenty of opportunities to use different Gs to perform G.B analysis, or to tilt your crystal to different Gs to get information about the arrangement of defects and their interactions in this specific area. So one of the examples here, we want to find out what are the individual dislocations in the slip band. So similarly to conventional TM in STEM here, we do a 2-beam diffraction condition, different Gs, different tilts. We can do G.B analysis table and visibility and invisibility conditions, and we can figure out what kind of Berger's vector these partials forming dissociated 110 half 110 has. So this is very complementary to CTEM. So now we were talking about structure being tilted at the angle. We are using larger field of view, similarly to CTEM, bright field, STEM, diffraction contrast imaging. But as I said, our starting point was edge on zone axis. So let's go back to zone axis. Let's tilt that object back to zone axis, and let's see what other opportunities we have when we are using probe-corrected STEM for such investigation. So now I'll be talking about atomic resolution out of STEM in combination with COS. So when we are using high def STEM, we switch the camera length, and we are our contrast, our image is formed by electron scattered to high angles. And there's huge benefit, especially in atomic resolution study of these defects, because in high def STEM, the images are interpreted directly in terms of atom types and positions, and basically your contrast of where the atomic column is sitting, the closer that your conversion probe is coming to the atomic column position, the more scattering you're getting. So the intensity and signal in contrast are increasing. So where bright spot, where the contrast, the high intensity contrast is, that's where the atomic column position is. That's very big difference from the practical point of view compared to what we used 10 years ago, phase field high resolution TM phase contrast, where you had to do simulations to support and to find out where actually your defect and your stacking change, like the stacking sequence change in your complex defect was happening. So here, what we do just from a practical point of view, we were doing bright field STEM DCI. We just tilted to zone axis, changed the camera length, and magnify, and in few seconds, you're getting atomic columns of the defect. So that's huge practical advantage. So this is what you can get. So this is raw high def STEM Z contrast, but we can combine that with some other tools which are available to us today to deliver even better information about that defect, right? So we can do FFT filtering, get rid of unnecessary noise, and using fast Fourier transformation, and then we can apply some deconvolution, reconvolution steps to further enhance the signal to noise ratio, and then we can cross-correlate the data with simple calculation and to find where the Gaussian peaks with well-defined maxima are, and we can fit that or FFT filtered and deconvolution image, and we can obtain two-dimensional coordinates of the atomic columns, can identify them and tabulate them, and then we can work with this export of our bright field STEM or high def STEM data. So we can use center of symmetry. We can calculate center of symmetry for each atomic column, and basically it calculates how far every atomic column is from ideal crystal. So you calculate the parameter, and it can visualize. It's very sensitive to changes in stacking sequences. So it can highlight what kind of defect you are looking at. So here, this is simple Shockley partial dislocation, which is associated, which is bound to simple intrinsic stacking fault. Now, when we take a look at the analysis of the whole package of the whole twin embryo, which on the left, this is what you would classically see with CTEM DCI on the left image. This is how you would analyze such a defect structure. You would do G.B, you would do tilting, you would be looking for a change in stacking full ribbon. That's how you would be trying to find description of this this defect. But using STEM, using these advanced tools, we can go further in depth, and we can analyze this like cross-correlated approach nowadays can help us to decipher even very complicated defect arrangements and stacking sequence changes where in these alloys, with lowest technical energy or with precipitates, where complicated things are happening in terms of plasticity and deformation mechanisms. Here you can see with atomic resolution preciseness, you can resolve where you have transitions between intrinsic and extrinsic stacking faults, HCP stacking, or twin sequences. So this is a huge advantage. Another example, I got a lot of questions after the paper was published that in GRX alloy we study or we are trying to figure out the local chemical ordering, if there's a local chemical ordering, and we didn't find anything, but there were questions like, are you sure about? So it's known that if you have chrome gold nickel based alloys and you add elements as aluminum, titanium, niobium, which are L1,2 forming elements, local chemical ordering clustering can happen even in solution annealed state. So in chrome gold nickel based alloys, there are also other types of chemical ordering, but this specific ordering associated with aluminum, titanium, niobium, it's possible to very simply detect that using hot-of-stem. So this is important because this significantly affects mechanical properties and processing of such material. So this is an example of chrome gold nickel based alloy with aluminum, titanium, and niobium. And if we do STEM EDS, these order regions are very small and hardly resolvable. So if you do a standard map, it's very difficult to see them. You would say that there's nothing present. Even using line scans or long scans, high signal scans, you cannot detect it. But if you simply use hot-of-stem, it can show you presence of such ordering. If you just simply do a FFT diffraction pattern of your atomic resolution data, and you can see the diffuse spots, superlative spots related to L1 to order domains very nicely. You can go further and use the FFT filtering, and either using all the spots from both phases, or you can just do inverse Fourier transformation using just superlattice diffraction spots and visualize these order domains, which are of size like 3 nanometers. So this is another use of hot-of-stem to deliver like important information, important answer for questions and topics which are being studied now in structural materials. For our GRX alloy, again, when I show the results, we don't see any superlattice diffraction. So when we compare to the alloy we did the experiments, we are pretty sure that no ordering was present there. There was another question which we got, and that was about vertical and horizontal streaks associated with that FFT diffraction pattern which we obtained from atomic resolution image, and we are pretty sure that this is just this is not associated with chemical ordering present in the alloy, and it's just artifact which is associated with conventional rastering pattern, which is set standardly from for the systems as they're produced, and it's also this can be also associated with drifts in specific situations. So if you're more interested about this artifact, please find the paper in ultramicroscopy in 2020. So we are pretty sure that we are not seeing any ordering in case of GRX alloy. So now let's move on to last of topics, and that's Stereostem Imaging. This is example which is associated with NASA alloy. So stereotransmission electron microscopy is quite old topic. It's been used decades ago, but now we can use these classical methods, and we can use these methods with new systems which are available, new STEM systems, and get even better data than when it was than what was possible with the conventional TM. So stereo TM or Stereostem provides a 3D impression of the microstructure and TM foil, and it allows us to perform depth and thickness measurements to decide whether microstructural features lies inside the thin foil or on the surface. And I definitely have to recommend this paper if you're interested more in theory and background of these classical methods used in combination with new instruments, and with using Stereostem to do characterization for this alloy. We have very good collaboration with Professor Antonio Doi from IPM in Brno. So let's just talk about how practically you can get the information and what kind of information you can get if you use this approach. So as I was talking before, we usually start with zone axis imaging. We do bright field stem DCI to image the structure. If you start from zone axis, this gives you a space to later tilt the sample to use two beam conditions, and that's what we are looking for. So we first collect the data with 101 zone axis, and then we tilt using 200 G band, and we tilt right, we tilt left, and based on theory to get nice 3D anaglyph for human eye for the visibility, the distance between these two images with two different tilts has to be around 10 degrees to have like ideal contrast and visibility. Obviously we use the same G, that's important, and some orientation of the G for the contrast formation conditions. And then using these two images, we use freeware software, 3D anaglyph maker, and we form this image. Then we take red cyan glasses, and we can see already the structure nicely, but we can quantify that further. So what we do is that we are looking at the anaglyph, and we put these two images of the structure with two different tilts into coordinate system, and we extract information about intersections of different defects with top and bottom surface of the foil, as we see it using red cyan glasses on 3D anaglyph. So we mark the positions of different defects scattered throughout the whole probed area, and we extract the set of data for top surface and bottom surface. And then from the geometrical considerations, we have set of equations which we solve using these coordinates, and using that we can use either a linear or a polynomial fit of the top and bottom surface of the foil based on these data. And basically for every pixel or every point we are able to identify on the foil using this approach, we can get thickness fairly precisely. And there's a huge advantage of this technique compared to, for example, if you're using eels to figure out the thickness. This is usually limited in metal samples to 150 nanometers. If you're using PACBAT, this is usually exclusively for very thin samples up to 100 nanometers. You have to do ultimate resolution and simulations. This method, classical stereo microscopy combined with STEM, we were able to get very nice images and thickness for metal samples, nickel-based, up to 1 micron, close to 1 micron, so almost 1,000 nanometers, and that's this fairly thick sample to be able to get information from. So when we know very precisely what's the thickness of the area we investigated, we can go further and we can cross-correlate this with STEM EDS, which we collected, for the same area, and we can figure out, if there are different dispersion of different objects which are important for us. Like in this case of GRX, it's oxide particles and stacking full tetrahedras. So both are expected to be strengtheners and obstacles for dislocation movement. So we are trying to figure out what's the volume dispersion, what's the mean distance between average mean distance for these objects. And so we can get the distribution functions out of it. We can get volume, particle density, and fractions of that, which can be used for later, especially for alloys which are produced for additive manufacturing. You can estimate what's in the initial state already like Taylor strengthening and Orwan strengthening factors for these alloys using this technique. Another thing which this foil thickness measurement and stereo microscopy can be used with is the estimation of defect and dislocation density. So here we are just using a statistical method from 1960, intersection method, and since we know very precisely the volume and thickness of our area of interest, we can fairly nicely estimate what's the dislocation or defect density for the area, and we can estimate for the specific area what's the Taylor hardening factors. So this is a level of information we are able to get from that. And this brings me to the conclusions. So multi-scale characterization using various mutually connected STEM-based methods is an essential part of modern material science, engineering, and materials design. STEM-based diffraction contrast methods, as well as atomic resolution out of STEM, provide critical information about microstructure, chemical composition, possible ordering effects, and the nature of defects in modern materials. And it can be successfully complemented with additional tools, center of symmetry or stereostem microscopy, and precise local foil thickness measurements to further increase the quality of information. This electron microscopy-based multi-scale characterization delivers about the structure of materials. So thank you very much for your attention. And if there are any questions, I'll be very happy to answer them. Thank you.
Questions here, or if you're online, feel free to put some questions into the chat or on there. We'll answer those as we go along as well. So we started here while waiting for online as well.
Thanks, Milan. Wonderful talk. Thank you. Just amazing examples of how you brought all these techniques together for real impactful science. On the question of operating on its own axis, okay, system, then you have relatively thick samples by high resolution STEM, so certainly tens of nanometers. But you're in a strong channeling condition, and therefore the effects of both channeling and dechanneling could be very significant.
Yeah.
And so in two of the techniques he talked about, in both the center of symmetry imaging and also in the question of some sort of compositional ordering, that could be very important.
Right, I agree.
So in the case of the center of symmetry, have you considered or have you modeled the possibility that in the regions of interest, the atoms are not actually well aligned through the thickness of the sample, or in the case of the chemical ordering, if the chemical ordering is through the thickness of the sample, then the potential of the different atomic species is going to change the channeling condition.
Yeah, so yeah, you have to be careful. So first thing about this chemical ordering, so this is very specific to this specific ordering that it's just this aluminum. And basically we found out empirically, okay, this is how we can see it, and this is how we cannot see it, or it's there or it's not there. So if the superlative spots appear, and so we are like, we are counting on the fact that we are just probing, the volume, and it can be anywhere throughout the volume. And if it's there, it will pop up on the streaks. Obviously, we didn't do like any thickness, based experiment, like how different it'll be if we have 20 nanometers and 80 nanometers. That'd be interesting to do. But it's definitely something to consider. Like we believe that if we are probing the volume and if it's there anywhere in that volume, it'll just be visible in Fourier transparent in reciprocal space. So that's this specific type of order. Now about COS, that's more tricky question, definitely, and I think we have to be careful, especially if you're dealing with specific defect. Because when we tried night enter study, where where it's like more sensitive, it's more sensitive about the placement of atomic columns. Not every experiment went and like sometimes COS, we knew that the dislocation is there. We knew that COS was showing that the defect is there, but the night tensor was not showing it because of channeling or thickness associated defects. So it's definitely something worth trying to pursue. Okay. And it definitely has is playing a role. So if you're trying, I mean, COS, we are usually it's supporting technique, like for us. So it's not something like you have to be careful how to use it, and you have to be careful. You have to do some different experiment also, or different perspective to be sure that the answer you're getting is true or not. So we always validate using also a different approach. So center of symmetry is just supporting for us. But as I said, to be able to quantify more precisely channeling effects and thickness of the foil definitely can play a role. Definitely, yeah. So yeah, but no experiment has been done yet, to more like find out like what are the limitations and what to be careful about.
I think even the simulations that one might try, with using the Les Allen type approach, I think your thicknesses are too great for even those simulations to be really reliable. So yeah,
I agree. Yeah. So that twin embryo I was showing, that's 500 nanometers.
Yeah. Yeah, that code's not, without beyond 10, 20.
But for that, like when I was showing the COS and the distribution of different stacking sequences and positions of partials, fortunately we were able to validate it using just tilting experiments and looking at the defect, like from side and doing different G's and the ribbon fringes. So we have that validated for this specific case. Obviously, it took a lot of work hours, but there are also cases where it didn't fit together, like in terms of COS. So yeah, I agree. The one has to be careful.
Yeah, thank you.
Yeah, Mike just chimed in and said, not sharing by the entire thing as a sample.
I'm sorry?
Mike Mills just on the chat is that yes, granted there will be effective defocus value.
Yeah.
That we could talk about. So
yeah,
nice discussion.
Like if I may have one comment, like from practical, like user point of view, if you do defect studies, it's always very thin balance between thickness, the area you're trying to study, because if it's like really thick, then the diffraction contrast, like on lower magnifications, is nice and it's easy. Also, like the defects are, nicely resolvable, but as you get to thinner and thinner area, then you're getting other effects, and you're getting like the surface effects of foil. And then the question, like, what happens with, the dissociation of the partials? Like, are you getting through, representation of the defect structure you're looking for? Or so it's always tricky. Different alloys, different materials. What's the thickness to use for samples to get the answer you're looking for?
Yeah. I saw a question online. Abhishek's excited about trying this out himself, but he's also wondering, so while long-range local ordering can be clearly identified using Stereostem, was wondering, what are your thoughts on possibilities of identifying short range ordering?
Yeah, this is just, as I said, it's very specific ordering, which we empirically found out, okay, we can detect that specific ordering. But, you know, when we were talking, I was talking about chrome nickel based alloys here. And there are different types of ordering, which obviously cannot be detected by this. And you have to use different techniques. And, you know, there are energy filtered TM or, you know, 40 stem is being now investigated, like what kind of answer it can deliver for ordering, you know. So the problem is that, you know, last High Entropy Alloy Congress, there was a very nice talk that we there's so many different types of ordering which you can have in alloy. And so first, what we should be looking for is to define what are the differences between these orderings, and then to find proper techniques to be able to, you know, detect them. So I think there's a little bit of confusion still, you know, in the field, like what kind of ordering we're talking about, and is this like ordering, or is this initial is this initial stage of nucleation of secondary phase, and can we like differentiate? And so, you know, first I think we should resolve these questions like from the metallurgical point of view, and then based on that adjust experimental techniques to be able to detect them. So, but yeah, as I said, you know, when I was talking about the reciprocal space and superlattice spots, this is just very specific one type of ordering we can detect. We, like, you know, empirically proven. But different types of ordering, you know, it's the question.
Questions we have?
Do you have any comments on the sample prep? I didn't belabor the sample prep during the process, but what final processing steps you had to do to get the materials as clean as they were?
So for GRX, Tim Smith, you know, who was in charge of the GRX project in NASA Glenn, he did a very good job, you know, optimizing jet polishing conditions, twin jet polishing, and I know that these alloys are very tricky to optimize everything, but we got beautiful, you know, defect-free, contamination-free samples, and that the result you were able to see, you know, like when you have electropolished disc foil without any flaws, and you combine it with, you know, proper system which has monochromator and you know, state-of-the-art detectors, you can get like beautiful contrast. Regarding FIB foil preparation, that's a question to Veronika Mazanova, who's you know, doing who's the expert. But yeah, here that's a long process. You know, like the more time you spend with preparation of the foil, if you're doing FIB foil, you know, tuning or thinking about what will be the orientation and how you'll work with that orientation, like what kind of G's you'll be trying to investigate, where you'll be trying to tilt. That's important to think about before even you go to plug the foil. You know? And a lot of people underestimate that. They underestimate how important is the FIB foil preparation to the outcome at the probe corrected TMITs. You know, like it starts there. You know, the better FIB foil, better thought through process you involve there, the easier life you'll have at the you know, at the state-of-the-art instrument with probe correct. So yeah, but specific details, they differ. You know, different alloys, different question you're trying to find answers for. Like you have to optimize your workflow based on, you know, what you're trying to investigate.
So for your bright field images, did you use a lower camera length and use a dark field bright field, or did you use a higher camera length like the bright field had in like a smaller group?
So I mostly, like, if the sample are thicker, we mostly work with bright field because it's easier to just use transmitted beam and to adjust the convergence angle to get the transmitted beam into bright field, and then the diffracted beams to shield them out. So it's easier, and if the sample is thicker, then it's they're not such big issues. If for annular dark field detectors, that's much more trickier, especially if you're doing weak beam STEM, using dark field detectors. You have to play with convergence angles, because in STEM you have to deal with overlapping disks and of the 2G, 3G, 4G diffraction. So to get like perfect dark field, diffraction contrast, that's much more work you need to put into it, and then based on your specific material and specific imaging condition, you have to optimize that. We've seen it with JP Cousinier, who was here working on BCC high entropy alloys. We are trying to image the dislocations in this very dense field of coherent precipitates, which were all scattering a lot also. So it's very difficult to image dislocation lines, and we have to play a lot with objective aperture, convergence angles, setting of the stem to find the optimal conditions for that specific alloy and that specific orientation and that specific case. So yeah, so bright field easier, dark field if you want to get nice data which you trust, more difficult.
Okay, last question and we'll wrap it up.
Thank you, Milan. Let me echo David's comments. Just extraordinary imaging right across the board. Given that you could see the L12 superlattice structures, I'm intrigued that you couldn't detect them in the X-ray maps. What's the challenge there?
So first of all, from practical and time-saving purpose, we just did like the STEM EDS scan with specific parameters. Mm-hmm. But I'm not saying that it would not be visible using properly set up atomic resolution, but atomic resolution EDS using proper corrective system. I think it would be possible, but the time and work which would be needed to input into that, to accomplishing that task is too much. It's easier just to. So that was my reasoning. Like if you do like normal scan using I don't know, like normal settings. So you orient your crystal, you have your place, and you just set up the scan with reasonable resolution, but it's not atomic resolution on a random sample. So the sample is not specifically prepared for atomic resolution EDS. Then you'll not see it. But you can optimize your experiment and workflow in such a way that you already prepare your fit foil, thin and oriented, and so it'll be specifically prepared for atomic resolution STEM EDS. And then you'll optimize your conditions on the system, on an instrument for STEM EDS, what Ashton is doing here for superalloys. But this will take a lot of work and a lot of time. So it's just practical reasons.
Thank you.
Thanks again, Milan.
Thank you.
So feel free to grab our donut, grab some more coffee on the way out if you're in person, online. Thanks for showing as well. We have these once a month. So next month, Sarah McCullough is giving a talk on spy-related work, followed by XPS, and then I'll be giving a talk on flat diffraction at the end of the semester. Okay. See you guys next month.
So, Dan, should I turn it off?
Yep.